time to dive a little deeper into the normal distribution. Now, as I alluded to in the last lecture, many numerical variables naturally follow a normal distribution, or a bell curve. Now, normal distributions are symmetrical around the mean and have no skew, meaning that the mean is typically equal to the median, with most of the data concentrated around its center and flaring out in tails on both ends. For example, let's take a look at all the Olympic basketball player heights in history. You can see that the data, or the frequency distribution here, is symmetrical around the mean, with most of the data near the center of the distribution, and then fading away towards the sides. And you can see this in human heights, in human weights, in IQ scores, in blood pressure, and many other variables. And since these distributions are so common, many statistical tests are designed for normally distributed populations, which is why we'll mostly focus on the normal distribution in this course. Now, the normal distribution is described by two values that we already know how to calculate and interpret: the mean and the standard deviation. And we can actually see that here, this is the probability density function for the normal distribution, which determines the height of the normal curve at any value x, given a mean, which is represented by this symbol, which is called mu, and a standard deviation, or sigma. And before this scares you, because it is scary looking, we won't actually use this formula as you're seeing it right now, don't worry, because there's an Excel function for it that we're going to use instead. But my point though is that if we assume that Olympic basketball player heights are distributed normally, which seems like a reasonable assumption given this distribution here, then we can take their mean and their standard deviation, pass it through this formula, and we get this line or normal curve, which as you can tell fits the data pretty well. And this line is now a model that we can use to calculate probabilities of Olympic basketball player heights. Now, these two values also describe the properties of the normal distribution. The mean determines its center, which makes sense since it's a measure of central tendency, and the standard deviation determines its width, which also makes sense since it's a measure of variability or spread around the center. So if we grab this normal curve here that has a mean of 180 and a standard deviation of 8, and then change its mean to 160, well then the center will shift to 160 and the width will stay the same, which also applies if we change the mean to 200 instead. Now if I stick with a mean of 180 but change the standard deviation, you'll see that if I make it smaller, then the curve gets narrower and taller, and if I make it bigger, then the curve gets wider and flatter. In other words, changing the mean shifts the curve along the x-axis, and changing the standard deviation squeezes or stretches the curve. So that's the normal distribution. Now let's quickly move over to Excel and see an example of this with our project data. Again, I am in the Excel statistics workbook, but now we're going to go to the links under the probability distribution section, starting with the first one on the normal distribution. And what we want to figure out now is if the final grade distribution for the graduates follows a bell shape. And in one of the assignments in the previous section, we had already created a histogram with the distribution of MBA grades. That's why I added that here already. So now let's just take a closer look at it and see if it follows a normal distribution. And it does look like it kind of follows the bell shape here, and it is relatively symmetrical. So let's see now if the mean is equal to the median. In other words, is the average value also the middle value? So let's calculate both of these, get the average of our data and the median of our data. You'll see that they are the same. We get 80.17 and 80.20, which is right around here, which is the center of my distribution. So it does look like all signs point to these grades being normally distributed, and it's actually not crazy to think so because grades do generally follow normal distributions. A classic example of this being SAT scores. So you can look it up online and you'll find that they very closely resemble a bell curve. So now all we need is to describe this normal distribution using the mean and the standard deviation. So we know the mean already. It's equal to this. And we know how to calculate the standard deviation. Close this. And there we go. So this right here is our normal distribution of MBA grades. Alright, so now that we know that normal distributions are described by their mean and standard deviation, time to talk about z-scores. A z-score indicates how many standard deviations away from the mean a value lies. It's a nice and easy definition, which in this case leads to a nice and easy formula. So to calculate a z-score for a value, simply subtract the mean and divide by the standard deviation, or you can also use the Excel standardize function. So if we look at the normal distribution of Olympic basketball player heights from the last lecture, this right here means that our variable x, which represents height in centimeters, follows a normal distribution with a mean of 195.2 and a standard deviation of 10.26. And say we want to know how many standard deviations taller than the average basketball player Michael Jordan is. Well, he's 198 centimeters tall, so if we plug that into our function, we get a z-score of 0.27. And we can show it like this as well in what's known as the standard normal distribution, or z-distribution, which has a mean of 0 and a standard deviation of 1. And just to show another example, let's take a look at Shaq, who, as it turns out, is a little over 2 standard deviations taller than the average basketball player, which is quite a bit, as you can see from the distribution here. Not a lot of basketball players are that tall. Now, let's jump to Excel and calculate some z-scores ourselves. I'm going to go to the z-scores link, and what we want to do is select a student from this drop down here and figure out how many standard deviations away from the average is this particular student's MBA grade. Assuming, of course, that MBA grades follow a normal distribution with a mean of 80.17 and a standard deviation of 6.17, which is what we defined in the last lecture. So let's bring over the grade for this student. We can do this a bunch of different ways. I'm going to use the VLOOKUP function. So I want to look for this value in this range right here. Well, in the left column actually of this range right here. And I want to return the MBA grade, which is on the second column here. So column index number is going to be 2. I want an exact match. Press enter. And we can see that student 8 has a grade of 88.7. And if I change this, say to 19, then we get 96.1. So we got our grade working correctly. Now let's calculate our z-score, and I copied over the formula from our PowerPoint presentation right here. So we want x, which is our grade, minus mu, which is our mean, and let me wrap this in parentheses, and then divide that by the standard deviation, which is this right here. Press enter, and we get a z-score of 2.58, which is quite high, but it does make sense given that this is one of the highest grades in the entire class, and it's very close to 100, which is the maximum grade. Now let's check another student. Got 25. He got a grade of 79.1, which is very close to the mean. In fact, only 0.17 standard deviations smaller than the mean. Now let me replace this formula with the standardize function instead, just to show that we get the same result. It's going to ask for an x value, which is a grade, a mean, which is this one right here, and a standard deviation, which is this right here. Close that, and we get, again, negative 0.17. Let's look at another one. And we get 0.73 here with a grade of 84.7. So those are z-scores for you, which in essence help determine how extreme values are in the context of their distribution, depending, of course, on how far away they are from the mean. And in the next lecture, we're going to cover the empirical rule, which is going to give us a better framework for interpreting these numbers. As promised, time to introduce the empirical rule. The empirical rule simply outlines where most values fall in a normal distribution. So around 68% of the values live within 1 standard deviation from the mean. Around 95% of them live within 2 standard deviations. And around 99.7% of them live within 3 standard deviations from the mean. So why is this relevant to us? Well, these are handy numbers to have in our mind to put some context around the z-scores. If we look at our project example, if a student has a z-score of minus 1.7, well then that's not unexpected since 95% of all students will fall within 2 z-scores from the mean. But if a student has a z-score beyond 2 or negative 2 though, then he's either performing really well compared to everyone else or really poorly. Aside from that, it's also a good way to check if your data is distributed normally, aside from just, eyeballing it using a histogram like we have before. And let me show you exactly what I mean by that in Excel. Here in the Excel statistics workbook, let's go to the empirical rule link. And let's say that we want to use the empirical rule to find out the grade intervals in which most of our students will fall. We have our normal distribution of MBA grades, so let's see which grades are within 1, 2, and 3 standard deviations away from the mean. So let's calculate these values. The lower bound or the lower grade here is going to be equal to our mean minus 1 times the standard deviation. And let me fix these two values with F4. Press enter. And now let's calculate the upper bound, which is going to be equal to, again, the mean, F4, and this time plus 1 times our standard deviation. F4, press enter, and let's apply these to the right to get our intervals for 2 and 3 standard deviations as well. So what do these numbers represent? Well, according to the empirical rule, if our population of MBA grades is normally distributed, then 68% of all students will get final grades between 74 and 86. 95% of them will get grades between 67 and 92, and 99.7% of them will get grades between 61 and 98. So what we can do now is check to see if these students from our sample are distributed in the same manner. So let's calculate that. We want to count, so I'm going to use countifs. The number of students here, or the number of grades rather, and let me fix that, that are greater than or equal to 74. That's our first criteria, and the second is that these same grades, fix those as well, also need to be less than or equal to 86.3. Let's close our function. So this is going to count the number of grades that fall within these bounds or within 1 standard deviation from the mean. But we actually want to get the percentage of grades. So we need to divide that by the total amount of grades. F4 one more time. Let's press enter. And let's apply this to the right. And would you look at that? These are almost exactly the same. So it turns out that we weren't too far off to assume that these grades follow a normal distribution after all. So now that we're safe to assume that, time for the good stuff. All right, time for the first assignment of this new section. And it looks like the good word on us is spreading because now we've got Nick Normal, the head of student placement, reaching out with this email. So let's read what he has to say. I just spoke to Molly and she mentioned that you were going to be able to make some predictions on student grades since they were normal or something like that. Could you do the same for me on the graduate salaries? Because it sounds like that could be something really beneficial for me. All right, so what are the key objectives here? Well, number 1, we need to plot the distribution of annual salary to see if it resembles a bell curve. Number 2, we want to check if the mean and median are equal. And number 3, we want to calculate the percentage of salaries that lie 1, 2, and 3 standard deviations from the mean to see if the variable follows the empirical rule. In other words, let's check to see if we can assume that the annual salaries of our graduates follow a normal distribution. Again, I recommend you try this out yourself and reach a conclusion, and then go on to watch the solution video after that.